Alright, give me a moment. I do need to set up the iPad screen because it's actually taking a bit of time. Hopefully this will not take too long. That'll be the best case scenario, but hopefully we'll get there. Alright, so just hang on tight. I'm putting up the screen in just a bit. Of course, I'll need to do a bit of trimming once the video ends. Okay, just hang on tight as I'm slowly going to set this up. Alright, there we go. Okay, let me just clean this up. And we are good to go. Alright, that's awesome. Let me change the pen color to white. Alright. Perfect. Alright, welcome everybody to the live stream. You can, if you're in the live stream, feel free to say hi. Feel free to put some W's in the chat. And whenever we're ready, we are ready to head off and do this paper. Now, this is a 2-hour paper, but I intend to finish this in 1 hour, so as the name suggests. And I hope to explain all of the different math concepts along the way as we get there as well. So, without further ado, hopefully this will be a quick and complete revision of all you need to know about calculus in this course. So let's start off with the first question. This involves evaluating this limit over here. The key idea is that when we substitute x equals to 3 in the denominator, we're going to get 3 squared minus 7 times 3 plus 10. And what we should get is, I believe it's 9 plus 10, that's 19, minus 21, that's minus 2. And the point here is that this is not 0. Since this quantity is non-zero, we will be able to simply evaluate this limit via a direct substitution. So let's substitute this limit. Let's replace each instance of x with 3. Clean that up. The top simplifies to negative 2. The bottom surprisingly simplifies to negative 2 as well. And this gives us the answer 1. And of course, you can mark your own answers. Give me a moment. I'm having a little bit under the weather here. Alright. Now, for this limit, on the other hand, we would expect to run into problems. Why would that be the case? Well, if we substituted x equals to 5 instead, you will get 25 plus 10, that's 35, minus 35, that's 0, which is rather unfortunate. This means we do need to do a bit more work in order to make this happen. The key trick here is to do a bit of factorizing. So let's factorize the denominator as follows. Since this here is x to the power of 2, the number in front is just a 1, we know that the two terms are going to be just x's. And this is a 10. So we could do a bit of guessing and come to the conclusion that 5 and 2 would be the candidates. We can subtract that. This will give us a negative 7 after we expand. And what that means is nice things happen because we get to do some, whoops, that's kind of unfortunate. Try that again. Nice things happen because we do get a bit of cancellations over there. So this simplifies to 1 over x minus 2. Now when we do the substitution, we don't run into any problems and we get our final answer. I don't think I'll give myself the marks, but you could give yourself the marks if you wanted to. Right, so hopefully that's a quick review of how we can compute limits when they don't look too obvious to us. So we start off with limits, and then the next question will be derivatives, that is differentiation. A warm-up practice, when we differentiate, we will differentiate term-wise like this. So we have 3 blanks, and there's a plus and a minus sign. We can copy and paste that. Now that raises the question, which is how do we differentiate each of these things? Well, for the first term, we're going to differentiate x to the 5. We're going to bring the power down and subtract the power by 1. This is known as the power rule. It is a common tool used in calculus. Now for the second term, we're going to differentiate the sine function, which simplifies to the cosine function. Another one of these classic results. And finally, how do we differentiate a constant? Well, the gradient of a constant is just 0, and therefore if we differentiate a constant, it's just going to be a 0 over there. So we can simplify the result. Oops, try that again. To get 5x to the 4 plus cosine of x. Now there's a similar result over here for the next part over here. So this result over here, given this particular expression, we need to calculate the second derivative. So in other words, we're given fx and we need to first find the first derivative, and then we need to find the second derivative, and finally we need to substitute x equals to 2. So that's not too difficult of a task. We can differentiate each of these terms one by one. So differentiating x squared gives us, differentiating x squared gives us 2x. Differentiating 2 times e to the x is 2 times the derivative of e to the x, right? It's 2 times the derivative of e to the x. And how do we differentiate e to the x? Well, that's just e to the x. This means we can differentiate a second time. Hi Marsha, hi Mahi and Emily. Nice seeing everyone here. Right, if we differentiate 2x, that would just be 2. Let's just do that. If we differentiate the 2x, we're just going to get a 2. And if we differentiate 2 times e to the x, once again, oh, hi Legolas, then we are going to get 2 times e to the x. Okay, now what that means is when we substitute x equals to 2, the result here is 2 plus 2e squared. And for this particular expression, we don't have any trigonometric terms, so we can just leave it as it is. If we do have some trigo terms, we need to use our calculators to approximate it, of course in radians mode, as always, because that's a common source of error that many people can make. Okay, fantastic. So that's just a quick warm-up of differentiation. Hopefully you guys are following along pretty well. Now for the chain rule, we need to differentiate the sine of x squared. And whenever the question uses this notation, this always means sine of x squared. Really, they should just put the brackets. It's kind of ambiguous, it's annoying, but it is what it is. So we're going to do that. So let's differentiate using the chain rule. Now, how do we differentiate this guy using the chain rule? Well, there are 2 layers to this expression. There is the sine layer. Let's write it this way. there is the sine layer, and then there is the x squared layer, which means we need to differentiate it layer by layer. We have a question, can we leave this 2 plus 2e squared as the answer? Yes, because there's no trigonometric terms. There's no sines, cosines, and tangents. If we do have that, then we will run into problems. Alright, for this question, so we need to differentiate the sines followed by the x squared. Let's do it layer by layer. So we'll differentiate the sine to get a cosine. We're going to keep the x squared here. And then we're going to differentiate this x squared on the outside. Perhaps using colors helps to illustrate the process. In fact, using the iPad is way more streamlined than using Windows-based devices. Anyway, we're going to go back to this question. So this will be cosine of x squared. And we're going to differentiate x squared to get 2x. Like this. So let's just simplify it very nicely right there. Alright, so there's a quick review of the chain rule, which refers to differentiating layer by layer. We have a related question on the bottom here, which is to differentiate the same thing, but now with this extra power of 5. It's surprisingly straightforward because how do we evaluate this guy? Well, this is once again differentiating the outer layer followed by the inner layer. Right? So the outer layer is the power 5, and to differentiate the fifth power, that would be to bring the 5 down and decrease its power by 1. From that, we will copy and paste the inside and differentiate this expression. Now, if you recall, this was basically the exact same expression as this guy over here, which means that we can just duplicate the answer. Like this. So it simplifies very nicely. The 5 and the 2's combine to a 10. I'm going to write this as sine x squared all to the power of 4. And then a cosine x squared over here. So hopefully that's a quick review of how to do the chain rule, which basically refers to layer by layer differentiation. Alright. Now we have the product rule, which I would like to think of as piece by piece differentiation. You could follow the formula in the given formula tables, or you could just use, I guess, understanding and sort of the habits of doing the product rule. The way I would do this is to think of it in this way, right? We have two terms. We have term 1 and term 2. So the idea is that we first need to differentiate the first term, keep the second term constant, then differentiate the second term and keep the first term constant. Now to differentiate the first term is to differentiate x, that's just 1. And to differentiate the second term, well, that's just differentiating the tangent of x. That simplifies to secant squared x. Hey Karudi, it's been a while. Yeah, it's been a while since I came on. We met in a university. He's making amazing math publications. Proud of him. Recently got married also. Congrats by the way. And by recently I mean about 1 year now. Anywho, where were we? Yes, so 1 times tangent of x, let's simplify that. That is the tangent of x. And x times secant squared of x. That just simplifies the answer like that. Okay, so it's a pretty straightforward recalling use of the product rule. Likewise, we could work with the quotient rule. Oh, it's not in math publications anymore. We gotta catch up one day. Okay, let's do the calculation here. Now, the way I do quotient rule is to first take the entire denominator. I'm gonna call this the first term and the second term. I'll take the entire denominator and I'm gonna square it. That's part of the use of the quotient rule. On the numerator, we basically do the same thing as product rule, except that we do a minus instead of a plus. And what does that mean? So instead, we're gonna do a differentiate the first term, keep the second term constant, minus differentiate the second term, keep the first term constant. Now to differentiate the first term, that's differentiating x. To differentiate the second term, that is to differentiate the tangent of x. So that simplifies to tangent of x minus x secant squared x all over the square of tangent of x. And there doesn't seem to be a simple way to simplify this, so this looks just about right. So that's the use of the quotient rule. It's been a while since we've done this live stream. Yes, I do feel quite rusty in this whole process. Okay. So let's do some term by term integration. Alright, let's do a bit of a warm up here. We have 3 terms, so we're gonna do the 3 terms like this. And we can integrate them term by term. Now to integrate the x squared, that is to raise the power by 1 and divide by the new power. This is once again the power rule for integration. Okay? To integrate tangent of x, we might need to refer to the math table and whatnot. I'm actually going a little bit by my own memory here, but the answer is the negative ln of cosine of x. Okay. And to integrate a constant, it's not 0. I know some of you thought there's a 0 there, right? So this is the integrate tangent of x. To integrate a constant, that's not 0. Right? That's differentiating the constant, you get 0. But to integrate a constant, you will take that constant multiplied by x. And if we leave our answer in this way, we might run into problems because we need to remember to add the arbitrary constant of integration. That is what this plus c means. Let's simplify all of that to get our answer. For those wondering what's with the 1/3 here, it's a preference. I like to express my answer as a constant times a function as much as possible. Okay? If you left it as x over 3, if you left this as x cubed, over 3, this would still be mathematically valid and therefore received well. It's amazing, exactly. Right? We're here to get as much of those marks as we can. Now, for the second term here, we once again want to do term by term integration, like this. But the important insight, as some of you might be aware, is that this guy here is 3 squared, and this here is 2 squared. Okay? So, yeah, I'm actually not using the math table, so that's that. Okay, so the first term is to integrate. We're just going to do it this way. 3 squared plus x squared. While the second term is to integrate 1 over square root of 2 squared minus x squared. There are a few ways to derive these integrals. Of course, you could have the math table to help you. You could use a u substitution if you wish. But we will just use the common results. That tells us the first one simplifies to 1 over 3 tangent inverse of x over 3. And the second one simplifies to 1 over 2. Oops, no 1 over 2. It's just sine inverse of x over 2. Finally, you want a plus c as well. So it's a quick use of the sufficiently basic integrals that we might be familiar with at this level. Okay, so just a bit of a warm-up. You might want to find a place to be able to... partial fractions takes a bit of effort. Partial fractions takes a little bit of effort over here. So we won't use partial fractions, at least for this particular... for this problem. Yeah. Now with the U substitution, we can make the substitution. So we want to use a U substitution to solve the problem. You could have been able to solve it without it, but why not? They gave us this particular expression, which tells us that we need to differentiate to get 2x. Now, just so that people online are not going to slaughter me, I do know that sometimes I explain it in a hand-wavy way, but what I'm presenting here is basically what we're familiar with. I'm going to put the x dx on one side and the half du on the other side. And the reason why I say that is because we can replace this x dx with this half du over here. Okay, so we're going to simplify it this way. Instead of x squared, we're going to simplify these x squares with u's. And the dx, right, the x dx, as I said, these two will simplify to a half du, notationally. Yeah. This recording will be on the channel, so you can feel free to revisit this whenever you want. Okay? I'll probably redirect future students here as well. Yeah, it's not the best mathematics. I'm kind of aware of that, but you know, this is just calculations. We're gonna integrate secant of u, tangent of u, and I hope that some of you remember that this is precisely the derivative of the secant function. Of course, we need to replace this u with an x squared. Okay, so that's pretty useful stuff there. All right. Okay, now interestingly enough, this is closely related to the next question, which tells us to evaluate this integral, which means we take this particular result and substitute it. Now we have these numbers over here, so this will be from 0 to 1. Therefore, we need to make the calculations. This will be half of secant of, try that again. Half of secant of 1 squared minus half of secant of 0. Now, secant of 1 is basically cosine of 1 over cosine of 1. And the secant of 0 is 1 over cosine of 0, which is just 1. Now, on your end, you do actually need to calculate this. I think I can actually calculate this using my computer calculator. Let me just do a quick computation there. This simplifies to 0.42540, which approximates to 0.425, corrected to 3 decimal places. I think some of us have done this exact same question before, but I guess we can treat this as a period, as a time to revise. That kind of works as well. Okay, technically we don't have a lot of time left, but I think we can manage. I think we will be able to complete this paper in 1 hour. Okay, including all the explanations. So we don't have a lot of time left. Now for B1, again, you can run through a whole calculation. If you substitute 7, the denominator will be 0. So the key trick here is to factorize the numerator and the denominator. Some of you might use L'Hopital's rule. Go ahead if you know how to present your work. I'm not going to stop you. But in any case, the numerator should be 7 and 4, and this should be negative and plus. You could use a calculator to derive this. You probably want to do this using a bit more time than myself, but I'm kind of working under time constraints here. So we can factorize that. and we can substitute x with 7, which gives us the answer 11 over 6. Alright, the answer here is 11 over 6. Great. Now for this question, we encounter the classic square root type of limit, which tells us that we will need to do a bit of conjugation. Now this term here looks a bit annoying, but don't worry about it. Just calm down. We'll get there. We're going to multiply this whole thing with the exact same expression, except that instead of a plus sign, we're going to work, minus sign, we're going to work with the plus sign. The reason we want to do it this way, 7 marks for that working. That's 7 marks. Yeah, feel free to add more working if you wish. Now the reason for that is that the numerator simplifies very nicely into an expression of the form a squared minus b squared and we expect nice things to happen. Some stuff should cancel out some way or another, and we should be good to go. So the squares definitely cancel out. 8 minus 9, right? This here is 9, right? This is 9, so 8 minus 9, that is x minus 1. And while this looks like it's not actually that straightforward, we actually do have one more trick up our sleeve over here, which is to factorize this guy into 1 plus x, 1 minus x, and of course we can pull out the negative symbol like this. So I'm going to do that. And then, very nicely, a bunch of things cancel out, which allows us to solve. Of course, you guys need to pay attention to your notation as well, right? I do notice some notations in the previous assessment were not the best. Now, this simplifies to 2 times 6 on the denominator, so I believe the answer is 1 over 12. I believe the answer here is 1 over 12. Alright, so feels good, and it actually did not take us too long to do that. But the key trick here is the factorization over here, as well as the factorization of the 1 minus x squared. Right? These two things combined help us obtain our final answer. Again, you could use L'Hopital's rule here, but I wouldn't in this context. Yeah, it's a little too troublesome. Alright, great. Now let's do this particular one. I believe some of us actually have tried this question before, but we can try it again, because why not? We're going to use this particular suggestion and calculate this integral. So let's do that. Now the integral here is the integral of tangent of, well, the tangent cubed x. So we're going to write this as, we're given this formula, right? And this formula is going to help us one way or another. So let's do that. Now there are a few ways to go about solving this particular integral, or rather evaluating this integral, but I like this approach where we put this as tangent of x multiplied by tangent of x all squared. Or let's do it this way, tangent squared x, because we can use this particular substitution. Right, we can use this particular or rather we can make that replacement. And there are actually multiple ways to proceed from this point on, right? There are actually multiple ways to proceed. I would say that the easiest approach is to just do a bit of splitting. So expand out this expression and then split the integrals. You're going to get tangent x secant square x dx minus the integral of tangent x dx. Now this guy, I think we've actually seen this integral just now, right? The integral here was actually the negative ln of cos x, right? But this integral is the slightly more interesting integral, right? Now, how do we actually evaluate this guy? I'm gonna just do it on the side over here. I'm going to use the substitution u equals to tangent of x, because if we differentiate, you actually get secant squared x. Right? And what that means is that you integrate, if you make the replacements, the tangent x here becomes a u, and the secant squared x dx becomes a du. Okay, which simplifies to half u squared, which is just half tangent squared x. And that is actually this component over here. So let's simplify. And that is the answer. Right? So it does take a little bit of creativity, if you would, in order to evaluate the integral, but it's not as crazy as it initially looks. Alright. So that's that. Okay. That was interesting. Now, part B is one of those questions I really enjoy doing. It's because I actually gave this as a tutorial exercise, as one of the extra exercises for my classes. So, not in the direct form, but in a modified version, right? It's a very similar problem that was done. So this question here asks us to evaluate this integral. Let's write that down over here. And we want to use this substitution u equals to ln of theta. Right, so this guy will become a u later on. Right? In fact, we can just plug that in. But now we need to work with the theta. Now, how do we do that? Well, the strategy we're going to take here is that we're going to take e to the u on both sides, or take the exponential on both sides. The exponential and the logarithm cancel each other out. This allows us to do some differentiations with respect to u. Now, if we differentiate e to the power of u with respect to u, it's just e to the u, right? There's nothing really that different. So d theta, keep it all as e to the u du. So that people don't stone me, I'm going to put this in quotes. Because now we can make the replacement eu du. And this looks like an expression which requires us to integrate by parts, right? Integral of a product of two items. Okay, and they don't really look very related to each other. So we're gonna do it this way: I S I D. And which one are we gonna integrate? Well, we're gonna integrate the exponential, right? Because according to our helpful tool here, the exponential term is here, the trigo term is here, and of course we try to integrate whatever is on the right side. So we integrate e to the u. We're going to integrate this guy to get e to the u, copy and paste it. Now, the sign of u, the sign of u here, two things happen, right? It remains the same and gets differentiated. Alright, so this simplifies to e to the u sine of u minus integral of e to the u cosine of u du. Now, what does this tell us? Well, this actually requires a second round of integration by parts. So let's do that. Once again, is minus id. We will integrate this guy and differentiate this guy. Right. So when we simplify, we'll get e to the u sine of u minus e to the u cosine of u minus integral of e to the u sine of u du, because a bunch of things cancel each other out. Well, then things get pretty alright from here. Okay, let's see. We do see that this term over here actually equals this term over here. So we can do a bit of algebra the algebra would simplify each other out. The integral of e to the, 2 times the integral of e to the u sine of u, if we bring this guy over to this side, right? That would equal, well, du. That would equals to eu. Let's do a bit of factorizing. Right? And finally, we can divide by 2 on both sides to get our answer plus c. Yes, you cannot forget the plus c when doing the integration by parts. Okay, so it's kind of messy, as you can tell. That's usually a sign of a good question done. A question done rightly tends to be messy, but that's a good indicator right over there. I would upload all of this later on, so you can take a look at the solutions if you wish. Right, feel free to let me know. In fact, I'm not done yet, right? Actually, the problem is not done because we actually need to solve in terms of theta, not in terms of u. So we actually need to do one more step and convert all instances of u's into thetas. There we go. It's a little messy, but gets the job done. This definitely gets the job done. Okay, fantastic. Alright. Now this is the integration by partial fractions. And it looks kind of challenging, but it's not as crazy as it looks. In fact, I like to solve b first because we already have the partial fraction decomposition. And therefore we can actually do term-wise integration. And secure some partial credit over there. Now, we probably want to solve the whole question anyway, so let's start with this guy over here. We can clear the denominators, so we can multiply that throughout the whole expression. I'm going to rewrite this x squared minus 4 as x plus 2, x minus 2, because we want to see some stuff cancel out. So this will become x minus 3 well, looks like I need a little bit of space. Alright, now based on this decomposition, a bunch of things would cancel each other out. And so we're left with x equals to a, x squared minus 4 plus b, x minus 3, x minus 2 plus c, x minus 3, x plus 2. What this means is that when x equals to 3, these terms would go to 0. So when we substitute everything, we get 3 equals to a times 3 squared minus 4. So a would simplify to 3 over 5. Right? Now, likewise, x equals to 2 and x equals to minus 2 would give similar kinds of results. For x equals to 2, well, these guys are going to go to 0, which means that we're left with the c term. So 2 has to equal c times 2 plus 2. This means c equals to 1/2. Right? And likewise, for the last term, I'm going to let you check that this would help us recover the b term. This one looks a little bit difficult, right? Because it's minus 2 minus 3 and then minus 4. So b is minus 1 over 10. It's a little bit weird, right? But the upside of doing all of that is that we just need to plug in these numbers. Oops. There we go. And that is the solution. Like, that's it. Right? So the idea is that once you have the decomposition, then the integration becomes very straightforward. Right? This is what we call integration by partial fractions, and there is a systematic way of how to even, let's say, derive this guy in the first place. There is actually a systematic way to that approach, but we won't be discussing that in detail, at least in the context of this course. Now, the slightly more interesting part of this question actually is part C. Okay, so we need to use this answer from part B and an appropriate substitution to evaluate this rather bizarre expression. Now, at this point in time, it looks really strange. And what have we actually calculated, right? We have actually evaluated this thing, right? So I'm going to rewrite this answer because I'm trying to do some detective work in order to suss out the substitution of interest. Well, this is part of the problem. Alright, make sure you check your work again and again and again. You want to score like a 70, a solid 70 in order to clear the papers. Now, this is the part which looks horrible, but I think there is a clue, right? There is a very important clue in this discussion over here, which is this cosine, right? We see a cosine minus 3 here, and there's something really suspicious about that, right? So I'm going to guess that that is going to be the key component that helps us answer the question. Now, we are going to do that, so let's make the substitution. U equals to cosine of x. Right, so then that actually becomes this becomes u minus 3, right? This becomes u minus 3. That's really nice. Yeah, for 3 marks, that's a lot of work, but it's fine. It's alright. It's not too bad. So this is the part over here which is a little bit more interesting, right? Now, at this point in time, well, what's 3 plus sine squared x? Well, it's kind of strange because we don't really know what to do here until we remember that sine squared x is 1 minus cosine squared x. Alright, which means we get 4 minus cosine squared x, which is 4 minus u squared, which looks a lot like this expression. Not exactly the same, but it looks a lot like it. Which tells us that the sine 2x there also has a trigo-related solution, which is 2 sine x cosine of x. This gives us 2 sine x u. Alright, so we can actually substitute this guy and even this guy. But what about the dx? What about the dx? Well, just like standard substitution, we differentiate to get negative sine x. Right? And so, that is the strategy we're going to use. In fact, if we look carefully, the du, or rather we can think of dx as 1 over minus sine x du. I know people are going to stone me for that approach. Oh, sorry, this should be sine x times u. My bad. Oops. This is sine x times u. So let's make all of those substitutions and magic is gonna happen. Something nice is gonna happen, right? We have to believe. There can be miracles when you believe. Okay. So this whole integral is going to simplify to the integral of 2 sine x u on the top. On the bottom, we're going to get u minus 3 and 4 minus u squared. The dx here gets replaced with this expression. Yeah, it's pretty interesting. And the sine x's cancel out. The 2 gets brought forward, and the minus sign can combine with the 4 minus u squared to, check this out, give us exactly what we have on the top right over here. I mean, you gotta admit, that is And it's pretty amazing. Like, seriously, that's actually really cool. It's amazing, right? So, we have that, and we can just use that formula to answer the question. Oops, this should be a u plus 2. Yeah, that's the solution. Let's do that. Plus c. Now, of course, u equals the cosine of x, so all we need to do is to back substitute everything. U equals to cos x. Takes a bit of effort, and I'm gonna just speed up the process over here. By just multiplying in the constant 2 as well. Okay. So with enough practice, it's all right. Again, you gotta be you gotta be patient, right? You gotta be patient. You've got to be able to sort of recall some of these trigo identities in order to help you out. Now I have only 9 minutes left for this discussion, although if you plus or minus a few more minutes, you could, what do you say? Yeah, we definitely can finish the last question, but let's try to finish this within 9 minutes, right? Okay, so this is the pace at which I like to go at when it comes to math papers. So we have this question. I believe some of my students actually have tried this before, and I believe we have a hack to solve this. But for now, we're just gonna go ahead to solve this. Now here's a bunch of questions which actually isn't really that important for us, right? The only important thing that we need to care about is this integral right over here. We need to evaluate this integral. This is one of these applications of integration. And let's go ahead to do that. Now, the real question is, how on earth are we going to start? Are we even going to start with this integral? It's really not obvious, okay? So that's the first observation to note. It is not an obvious problem. But I think with some thought, I noticed the 4s keep appearing, right? These 4s, these numbers, keep on appearing. So I would think that there is some kind of substitution involved with the 4. In fact, probably this whole thing gets substituted away. So my strategy is to replace all of that with the letter u. Now r here is a constant. So we don't have to worry, it's just a letter, okay? There's nothing too crazy about it. It's just a constant. Now if u equals to 4 plus r minus h, this means h equals to 4 plus r minus u. So dh du, that's just minus 1. Right? These guys are constants, so they go to 0, and dh is equal to minus du. On the other hand, we do know that over here we have h equals to 4, right? So when h, I'm just going to write to the margin. When h equals to 4, then u equals to 4 plus r minus 4. Now when h equals to 4 plus 2r, then u equals to minus r. I believe it's minus r. Yeah. We had minus r. So that means this f would simplify to instead of 4, right? Instead of 4, we're gonna get r, and instead of 4 plus 2r, we're gonna get minus r. This h is replaced with this guy over here, 4 plus r minus u. So let's replace this h with 4 plus r minus u. And let's replace the square root with that. The dh gets replaced with a minus du. Now one of these properties, well, I should not do that. I should minus 1 du. Now, one of the properties of integrals is that this minus 1 actually can flip this symbol over here. Like this. It is one of the properties of integration. Some of you are familiar with it, some of you are not. Right? And this tells us that we might want to do a kind of splitting. Right? So we're just going to split this in a relatively quick manner. Into two separate integrals. Okay. Now for the, where we have two integrals, I guess we could call this integral 1 and I could call this integral 2, right? So let's just calculate each of these integrals, and once we are done, we would have our final answer. So for this first integral, yes, I'm probably gonna need this extra space, right? Now for this first integral, there are a few ways you could do it, but perhaps there is a little trick up our sleeves, which some of you might have remembered / forgotten. If you look carefully, right, this looks like the integral of r squared minus x squared dx, right? I'm just changing the u with an x. And you might recall that if y equals to root of r squared minus x squared, and that certainly is the case over here, then we're going to get x squared plus y squared equals to r squared, which is a very special shape. This is the shape of a circle with center 0 and radius r. Which means we are actually calculating the area of the semicircle, which is just half of the area of the full circle. So that's how you calculate this integral. That is how you calculate this integral, at least in a rather time efficient kind of way. And in fact, I2 actually equals to 0, but without going there, maybe let's do the calculation as to why that's the case, right? U r squared minus u squared du. So the idea here is to compute yet another substitution. Let's use w equals to r squared minus u squared. dw equals to minus 2u, like this. And so du equals to 1 over minus 2u dw. Yeah, it's cool, right? I mean, this integral looks crazy, but it turns out to just be a circle, right? And the answer is pretty chill. Now, for this one over here, the du, we're going to replace that. And I'm going to just very quickly replace the limits as well. You should get... It's kind of awkward and embarrassing. I noticed that the limits looks a bit strange. Okay. Okay. So let me split this up into two more things, right? Let me just split this I2 into 2 bits. Minus r to 0. Again, this is really for technical reasons, because I saw something weird happening and I didn't really want to engage with that. Okay? So let's split this integral. Otherwise, we're gonna get some kinds of weird zeros, which I don't want to deal with. Okay? So, we can now therefore split up this integral. This one over here would become minus... okay, so this will become 0 and r squared. Alright? Okay. Yes. Okay, minus half square root of w dw. And this integral, okay, yes, I believe magic would happen here. Yeah, magic is going to happen, alright. Magic is going to happen because we're going to get r squared here and 0 on the top. Okay. And of course, we'll get the same thing. So it's minus half root w dw. Yeah! Alright, magic's gonna happen and there's no need for integration. Because, check this out. It's amazing. You can bring the negative sign out. But on the left here, we can flip the integral again because it's a minus sign over here. So we can flip the integral again. And when we flip the integral, check this out. We get the integrals, it's the same but of different signs. So it all goes to 0. So this whole work here, right, is I1 plus I2. But oops. It's I1 plus I2. Okay, give me a moment. It's awkward and embarrassing. Okay, there we go. We're back. Okay, so check this out. The whole integral here is just I1 plus I2, right? But I1 here is just half pi r squared, and I2 after we decompose and, you know, get our bearings and all of that, just equals 0. Which means this integral simplifies to 2, 4 plus r times half pi r squared minus 2 times 0. Which means the answer has to be pi times 4 plus r times r squared. This is the final answer. And just in time, right? Just in time. Evaluate F for a plate with radius 2 meters. So since the radius is 2 meters, we're just going to simplify this. We're going to substitute r equals to 2. And this would give us 24 pi. And that is the solution. Right? So that's how we do it. Right? There's 1 hour. Calculus in 1 hour. Alright, that was a mad rush. Okay. You could just write something, okay, for B4. Okay? So there's that. Just write something, and you know, if you write something that works out, you can still get some kind of credit one way or another. Alright, that's awesome. Okay. So maybe let's do a quick consolidation. Could you? Yeah, no, actually, no. Yeah, plugging the 2 at the beginning would have made life so much more easy. You are absolutely right. The numbers would have been a lot nicer. I totally agree with you on that. Okay. Yeah. I guess maybe let's do a quick run through of what we've discussed, right? As an overview of calculus. So this is limits, right? If you can calculate it immediately, do it. If you can't, do a bit of factorization. And for differentiation, split up as much as you can, and then substitute when necessary. For the chain rule, differentiate layer by layer. Even if there's 3 layers, 4 layers, 5 layers, just differentiate layer by layer. For the product rule, differentiate piece by piece. And likewise with the quotient rule. Likewise. For integration, split it up and recall some of your standard results from what you've learned in integration. And use substitutions whenever you need to. We used many substitutions in this discussion. Plug in where you need to, and of course, evaluate trigonometric expressions. Right? These are trigo expressions, you want to evaluate them. Same thing with limits, right? Remember that you can use this conjugate rule and do some factorization whenever you can, right? Do some factorization. With more substitutions. Sometimes you need to do your own substitution. That's fine, okay? Learn how to solve problems. Integrate by parts, ISID. Some of you are familiar with the DI method. Go ahead, it's pretty good. I love it. I just used it today. It's pretty good. It's actually pretty good. Partial fractions, right? Relatively straightforward stuff. Multiply, substitute some values, obtain A, B, and C. Then integrate. It's not as crazy. This one takes a bit of effort, but make the key observations. Always ask yourself, what's similar between the problem I'm trying to solve and the problem that they give me? Right? That is where you can find the solution, usually. And finally, a substitution helps with some interesting insights about integrals, like this one, right? This last question is going to test you on the fundamentals of integration, right? So what is integration at the core of it, and how do you make sense of the problem at hand? Right? And of course, some interesting insights tells us that some of these things actually cancel out, which is always a good thing. It's always nice when things cancel out. And that is it for this paper. If you like this video, remember to like, comment, and subscribe for more awesome videos to come. Not sure when it will be the next time I stream or make a video, but you can also check out the blog. It's all somewhere, somehow. Alright, thanks guys, and I'll see you guys when I see you.